And so it's a great pleasure to officially launch the BIU Astro seminars for the year 2021-2022 with an invitation from Almog Yalinewich from the Canadian Institute for Theoretical Physics, Astrophysics, to talk about shock ascension and the quest for core collapse supernova progenitors. Almog, go ahead.
So thank you so much for the introduction, and thanks for the invitation to give a talk here. So I'm going to be talking about core collapse supernovae, and the plan of the talk is going to be as follows. So I'm going to start by explaining what supernovae are. I'll try to convince you that you should care about them, even if you don't study them explicitly. And then I'm going to present two research avenues, two linked projects that aim to study the properties of the stars before they explode. And finally, I'll give the conclusion. So let's start by explaining what these supernova explosions are. So historically, when people talk about supernovae, they refer to a new source of light in the sky. So when you go to previous centuries, people describe supernovae, people looked up to the sky, they saw light, a source of light that they didn't see the day before. And this source of light got brighter over the course of a few weeks and then got dimmer over the course of a few months. Today, we know that these transient are the result of the explosions of massive stars. These are stars roughly more than seven times more massive than our sun, and they follow this trajectory shown at the bottom. They evolve according to a different evolutionary track that's different from low mass stars, and they explode and they end up as a relativistically compact object, so either a neutron star or a black hole in most cases. I should mention that when a star explodes, you have two, the aftermath can be divided into two parts. So one of them is called the remnant. This is the shock wave and the ejecta, and basically the cloud of debris that it leaves behind. And this is something that's depending on the density of the ambient medium. This is something that persists for tens of thousands of years to a million years in the most tenuous parts of the galaxy. And the other thing that they leave behind, as I mentioned before, is it's called the relic. This is a relativistically compact object. Now, this could be a black hole or a neutron star. And I also added this reservation here that you don't always get, I should mention that you don't always get this relic, because there are some rare cases where supernovae actually don't leave anything behind, even for massive stars. But I'll be focusing more on the cases when they do leave a relic. Now, the evolution of these massive stars could be very complicated because, first of all, as you can see from the evolutionary tracks on the left, the stars, depending on the mass, can cycle between very different kinds of forms with very different temperatures, very different radii. So they could cycle between blue, yellow, and red supergiants. And in some cases, some progenitors can start out with a large amount of mass, but they can lose a large fraction of it due to stellar winds. They can also be spinning very fast. They can have, most of them have companions. So all of these can cause the stars to evolve in a very non-trivial way. So when we see a supernova, one of the things that we would like to know is how we can take this information from the light that we see from the supernova and retrieve from it the properties of the progenitor. And when I say properties, I explicitly mean the mass of the progenitor, its radius, the mass loss rate, and also if there's a binary companion, and if it's close enough, then there can be mass transfer. So how much mass is transferred from one to the other. Now you could say, well, we've observed thousands, tens of thousands of supernovae already. Surely we can have enough information to answer these questions. And the answer is not so much. And the basic problem here is when you see a supernova, when it gets brighter, the star has actually been destroyed for about 2 weeks. And the reason for that is that when stars explode, they're opaque. So it takes a long time for the light to escape the dense envelope. And when it does escape, it's so long after the explosion itself that most of the time you don't even see the explosion itself. What you do see is the radioactive decay of nickel-56. This is the dominant isotope, and after it decays, then you see the other isotopes and so forth. So this mechanism is not so sensitive to the energy of the explosion. So it's not easy to take this information and infer from it the properties of the progenitor. This is the main hurdle in inferring the properties of the progenitor. Right. So after explaining what supernovae are, I want to try to convince you that you should care about them, even if you don't study them explicitly. So one of the main reasons people care about supernovae is that they produce some of the elements. So in this periodic table, you can see the different elements and color-coded according to what process produces them, what's the dominant production mechanism. And you can see that for many of the elements here that are colored in blue, these are primarily produced by exploding massive stars. And I want to highlight just one of them that I think you would agree is of particular importance to life. Another thing that supernovae do is accelerate cosmic rays. So these are very energetic particles that bombard the Earth, and above a certain height at cruising altitude, for example, they become the dominant source of radioactive radiation. And this is a concern for pilots and astronauts. Cosmic rays also bombard gases in our atmosphere, and they produce carbon-14, which is something that's used by archaeologists to date archaeological findings and determine from what period they come from. Another thing that supernovae do is that they regulate star formation. So here I'm showing two simulations, galaxy formation simulations, one on the right with supernova explosions and one on the left without. And it turns out that if you run these simulations without feedback, without supernovae, then you get too many stars formed too early. And from this, we learned that supernova explosions are important or at least one of the mechanisms that are important for regulating the formation of stars. So without these explosions, our sky would look different from what they look today.
Can I stop you for a second?
Yes.
So are you, two questions.
Yes.
Are you exclusively talking about core collapse supernova in this talk? Or are you referring to other types of supernova as well?
So I'll be focusing on core collapse.
All right. And then when you speak about star forming feedback, what are we seeing here? Is it a galaxy? Is it a cluster of galaxies? What are we seeing here exactly?
So here I think we're seeing just a cluster. But so when you talk about star formation, there are several mechanisms that might produce feedback, and supernova explosions are just one of them. So okay. There are So it's not so in different. I know what you're referring to. So in different cases, we know that different mechanisms. There have to be more than one mechanism, because we know that in some cases, for example, feedback starts too early, so it can't be from explosions. So in this case, in some cases, it's attributed to stellar winds instead. So what I'm saying is that core collapse supernova are one of the feedback mechanism, not necessarily the dominant in all cases.
Right. So how do you know whether this will be under what conditions this will be the dominant one?
So it has to be in cases where I think it would be the case after enough time has passed, right? Because we know that there's a minimum time from the beginning of star formation. There's a minimum time to get the first supernova. There's the salpeter time. So after this time has passed, then supernova become the dominant mechanism. Up until that point, winds are the dominant mechanism.
What about AGN feedback, for example? How is that compared to supernova?
So there's been some arguments in the literature for and against AGN feedback. So one of the problems with AGN is that in many studies and many simulations, what you see actually depending on the properties of the jet, in some cases what happens is that the jet breaks away from the right, just drills a hole through the gas and escapes into out into space. So again, it's not my area of expertise, but from my understanding, in many cases, the assumption is that although you have a lot of energy, that the coupling is very weak. So so in many cases it can't explain, it can provide the feedback, even though you do have a large amount of energy there.
It does opened up a cavity, a warm cavity. It's relevant for clusters.
Sorry?
Right. It's relevant for clusters, and clusters
Right.
can be quite substantial.
I see.
Okay, go on.
So another thing that supernovae are important for is the production of sources of gravitational waves. So as I mentioned before, the way to get relativistically compact objects like neutron stars and black holes are in supernova explosion. And when these happen close enough together or get captured, then they can become sources of gravitational waves. Which in this form, I don't have to elaborate on the importance of them. But so ever since the first detection in LIGO in 2015, we've made there have been a number of groundbreaking discoveries, including the discovery of the neutron star merger with optical counterparts in 2017. And again, all these sources are produced in supernovae. So understanding supernovae better would help us understand gravitational waves better or analyze the data better. Another thing that supernovae are important for, apparently life on Earth. So it turns out in some recent studies, people took samples from different layers in the deep sea crust, and they found anomalous amounts of a radioactive isotope called iron-15. And it turns out that this isotope is produced in supernovae explosions. And from this, they inferred that there was a supernova explosion close to Earth as recent as about between 1.5 and 3 million years ago. And if the supernova explosion did happen so close, then it's reasonable to assume that it might have had other effects on the biosphere, on the climate, and also on the ecosystem. Finally, I want to mention another application for supernovae as a nuclear physics lab. So it turns out that a few decades ago, when people measured the half-life of different radioactive elements, they made a mistake in the measurement of titanium-44. And the reason we know that is because people made observations of this supernova remnant of Cas-A, and they found traces of titanium-44. But when they measured the Likov didn't agree with the known with the lab data at the time. And by noticing it, people saw that there was some discrepancy, and they went back to the lab, did more experiments on titanium-44, and found that there was actually an error with the original data. So I find it ironic in some way that observing something that's light years away gives us better data than what we had in a lab where supposedly you can control all the variables. So after presenting some, trying to convince you that supernovae are important, I'll present some of my research and proposed research for the future in this area. So the first thing I want to talk about is the explosion mechanism. So a few decades ago, when the first computers were built, people tried to simulate supernova explosions. So they put all the relevant physics inside, they wrote a computer program, they ran it, and they found that instead of exploding, these stars would implode. They would collapse under their own gravity. And you can see an example here in the figure to the right, where the one-dimensional models shown in the dashed line, they begin by expanding out from the center, but at some point they stall and then they recede. They stop propagating. And for the longest time, this has been an issue, and people didn't know how to resolve it. And then a few decades went by, the computers got better, and people were able to run higher dimensional simulations, so 2D and 3D. And it turns out that when you run these simulations in 2 and 3D, then in some cases, sometimes the explosion do succeed. So you can see, as can be seen in the solid lines here. So here you see that when you run the same simulation in 2D, the explosion does succeed. But it's not clear why this would be the case. Why would something, because everything else was the same, why just adding more dimensions solve the problem? And the answer, well, at least part of the answer, was turbulence. When people looked at the profile of the shockwave, they found that it wasn't spherically symmetrical and smooth. It has this distorted shape. And instead of just moving in the radial direction, fluid elements moved in all directions. And this is something that by definition can't be in one-dimensional simulations, but can appear in high-dimensional simulations. And to summarize this, I've made this comic strip to describe the situation. So, right, you have the supernova shockwave that's produced at the center. It's competing against gravity, and on its own, it can't win. But when you add turbulence to the mix, then all of a sudden it is able to overcome gravity and produce a successful supernova explosion. And the effort here is to try to understand why this is the case. How does turbulence enable a star to explode? Now, before I go into the details, I just want to mention that this is a problem that's been studied in many groups around the world, and I'm mentioning some of them here. And most of the effort is focused on running very resource-intensive simulations of the shockwave itself. And I'm showing one example here to the right. Now, in addition to these efforts, to fully numerical efforts, there's also some effort in the analytic realm. So some of the authors, mostly by Sean Couch from MSU, he tries to simplify this problem by instead of considering a three-dimensional simulation, he tries to use the insights from three-dimensional simulations and incorporate them as extra terms in the one-dimensional simulation to reduce the problem, the dimensionality. There's another effort by Jeremiah Murphy from FSU, where he tries to use a one-zone model for the shocked region and build an analytic model from that assumption. And lastly, there's also Todd Thompson's group from Ohio State University, where they actually model the failed state, and they have a model where they try to describe a failed state, and when something fails to fail, then it means that it succeeds. When it doesn't fit the model, then they produce a successful supernova. Now, I just want to comment that all these three models, they don't, on their own, they don't explain, none of them explain how, they can't explain how turbulence helps a star explode. Now, there's also a number of issues with three-dimensional simulations. So,
can I stop you for a second? Before yes. You describe, or maybe you have it later, I don't know, the technical problems, the simulations, what physics is in these simulations? I mean, what is considered and what is not considered in them?
So they have hydrodynamics, they have gravity, they have radiation transfer, and nuclear reactions and neutrino transport.
And do they follow the chemical evolutions?
Yes.
So throughout, how many elements do they follow typically?
So they have networks with, so I don't know all the details, but they have networks of the order of tens of elements. This is what I've seen.
Okay, and how well do you know the initial conditions, or you don't really know? Namely, so what happens to the star just before it explodes?
So there are a lot of things we don't know, and most of what I've shown are just for non-rotating stars, which we know is not the case. But what I'm focusing here is on a more fundamental problem. Even when you have a model where even the imaginary model that we have in mind, even this we don't understand, even the simplistic model, right? Because the point here is that, right, we add turbulence, which at first glance doesn't seem to shouldn't affect the result, but it does affect the result. And I think so long as we don't understand why this happens, then considering a more complicated model won't advance you towards a solution.
What about magnetic fields?
So this is also an open question of whether how about what are the initial magnetic fields, what magnetic fields are formed in the during the process. This is also an unknown.
Is it considered as part of the simulation, or is it purely
some simulation? Not all. So definitely not all simulations. I've seen some simulations where they consider the formations of especially the ones that consider a neutron star at the center. They consider like the formation of a magnetar. But most simulations don't consider magnetic fields. At least most of the ones that I show here.
Okay.
Right, so I was going back to talking about the problems with the three-dimensional simulation. So first of all, it takes a long time to run. Second, it's very expensive. Even you need a lot of computers, you need to cool them, you need to pay for the electricity and so forth. But the most serious problem, in my opinion, is that different models don't agree on the results. And it's not just that they don't agree on it's not that they don't agree on very small details. It's not like one of them predicts a 5 solar mass black hole, another one predicts 6. You can see from here that they disagree on the outcome. There are some cases where some models say that the star explodes, and in some and different models say no, it actually doesn't explode, it implodes. Everything collapses to form a black hole. So they disagree also on whether you produce you have a direct collapse, whether you produce a neutron star, or whether you produce a black hole with a successful explosion. And
can I just ask if I understand correctly here? Green is neutron star,
yes.
Black is black hole, and it's not continuous.
No.
I mean, for the same model, I see that if I change the mass by epsilon, I can get a different result and then flip
Yes.
it back again.
Yes.
Is there some error estimate on these simulations, or is this just accepted that the astrophysical result is I guess chaotic or something?
It's accepted the astrophysical result is very, I wouldn't say chaotic because
unstable,
usually,
maybe.
Yeah, it's very what's the word? Erratic.
Maybe
yeah. Very sticky.
Continuing along this line, I mean, so you're saying that you're slightly increasing the mass, and then suddenly it does not explode, and then you slightly increase it further, and it does explode. Is there a simple reason of understanding why it behaves like that?
There's no simple one, but for example, one of the things that happen when, for example, when you add more mass, sometimes you make the winds more vigorous. So you can end up, so even though you started with a larger star, you end up with just the progenitor before the explosion could be less massive.
Because
so
it loses more mass before it actually.
But again, that's just one of the effects. It can't explain all the variability here. Right, because you add more mass, then you evolve according to the different. Then the evolution of the star is different. You produce the position of where the layers are different. I don't think there's a simple way of understanding why. Like I don't think there's a simple model that explains why you would have these gaps where they are.
I also have a question.
Sure.
So this is here you're showing the mass, right? But
the
I guess
initial mass.
Yes. And I guess this simulation depends on many more parameters.
Mm-hmm.
And do you see this behavior of like discontinuity in all parameters? Like, is there maybe one parameters where it is continuous, or do you see what I mean? Like, is it behaving this way of like turning on and off the explosion in a non-continuous way in all the parameter space, or is the mass something particularly where it behaves this way?
Yeah, so I understand the question. So I didn't run these simulations, just took them from another work. And so far, what I know is that the people have mostly looked at the age of the. So when you look at full simulations, they look at the just at the mass. They didn't cover other parameters. I do know there are other works where they looked, but these are more artificial. So in some cases, what people did is that they manually changed the properties of the of the energy injection. So in some simulations, what they do, they don't model the neutron star. They just say, well, there's some, they call it the light bulb models, where they just crank up or up or down the luminosity of the central source. And then you can go, well, then you also have this threshold behavior, right? When the luminosity drops below a certain value, then you go from a successful supernova to a failed supernova. And I think, well, hopefully I'll convince you that I was able to produce a model that explains why you have this dichotomy. Moving on. So again, this is because of all these differences, it occurred to me that doing more simulations won't get you out of this mess, because if you develop another simulation, you would just get another line in this figure. It won't get any closer to understanding what's going on. So for this reason, I chose to pursue a different approach. I developed an analytic model for these explosions, and these analytic models are based on the Taylor model. This is a model that was originally produced to infer the energy of the atomic bomb from known data, and it's based on the insight that if you look at the profiles, so here shown to the right, of the different hydrodynamic profiles of the hydrodynamic variables inside the shock region, you see that they're similar to one another. And this is something that you can phrase in a mathematical language, right? By saying that if you take the profiles at one time and you stretch them, then you can produce the profiles at a different time. And not only that, you can combine this with conservation of energy to produce a prediction for the trajectory of the shock. Now, originally, as I said, because the original application was for the atomic bomb, then the density profile was just uniform density, right? Because at the altitudes considered, the atmospheric density can be considered uniform. But it's just as easy to develop this theory for a variable density profile, so long as it's something simple like a power law. And from energy conservation, you can relate the slope of the power law to the trajectory of the shock. So what I've done is that basically I took the same equations and all I did was add just one more term. I added central gravity from a central point. So this is supposed to represent the protoneutron star that you get at the center after the core collapses. Now, in general, if you just do this, then you can't use self-similarity anymore. The introduction of another physical process breaks self-similarity. But it turns out that if you choose the right density profile, then you can recover self-similarity. So if, for example, in this case, if the density goes like r to the -2, then you can show that you get self-similarity and the shock front propagates like t to the 2/3. Now, if this looks familiar, is because the scaling you find here is the same scaling as Kepler's third law. So this is the law that relates the periods of the different planets to the distance and the distance to the sun. Yes, there's a question.
Yeah, I failed to understand something. You just showed us that the 1D models, the numerical models, do not work, and that they fail to produce explosions. So you need to have some turbulence. But the model, the analytical model that you're showing here is 1D. So why would you expect to have explosion?
Okay, so this is a perfectly valid. This is an excellent question, and I'll get to it later on. But the way that I introduced the effect of turbulence is by changing the equation of state. Because what I'm going to argue is that turbulence adds more stress, and this is effectively like making the equation of state stiffer. But that's a perfectly good question. Now I'll get to the details later on in a future slide. So okay, so I describe here a solution that I found, and by tweaking the parameters, you can get something that's solvable analytically. But the problem is that the fact that you find some solution doesn't guarantee that it actually represents a real physical scenario. But it just so happens that when you look at models stellar models, for example, here you can see over on the right, you can see a part of the star. This is a simulation of a supernova explosion, but the shockwave is somewhere over here at the distance of about 100 kilometers. At larger distances, you can see the profile of the star before the shockwave gets the unperturbed solution. And you can see from the slope here, even just by eye, you can see that it's not too different from the r to the -2 profile. So of course, this depends on the model of the star, but except for the very low end of the spectrum, this prescription that I described is actually described many real progenitors. So I was just lucky enough to find a solution that actually it can be used to model realistic scenarios. Now, you can go
just to make sure this -2 power law is for the density in the unshocked region.
Yes, it's the unshocked region. Inside the shocked region could be more complicated.
And in the unshocked region, then you can assume basically a 1D profile. It's not shocked yet. So
Yes,
there's-
yes, there's no turbulence there. It's moving. It's supposedly moving supersonically. Then, yeah. So in this case, then there's no turbulence there. Or if there is turbulence, it's much smaller than what's inside the shock region, so you can neglect it. Now, you can use the usual transformation, the usual way of reducing. What self-similarity does is take the partial differential equations that I showed you earlier, the flow equations, and it turns them into simpler equations, into ordinary differential equations. Now, to close them, you need boundary conditions. Now, instead of showing you the complicated expression, I'm just going to talk about the two factors that go into it. So one of them is the Rankine-Hugoniot condition. So these are just conservation laws that relate what happens on one side of the shock to the other side of the shock. This is the same thing as you would get in the classical set of Taylor explosion. In addition to that, there's also a complication here because of gravity. When a shock wave reaches a certain radius, it interacts with material that came from a larger radius because stuff starts falling before the shock gets there. And you can parameterize it using this parameter chi here, which is the ratio between the initial radius of the material and the radius of the shock when it interacts with it. And this number, this ratio, remains constant throughout the motion of the shock. Now, using these equations and boundary conditions, it's possible to integrate to do the integration and get the profiles for different. So I'm showing here different profiles for different values of the adiabatic index. And what's important to see here is that when the adiabatic index is very, and this relates to Asaf's question, when the adiabatic index is very small, all the material is concentrated on a very thin shell close to the shock front. Now, when you have once you have these shock profiles, profiles in the shock region, you can substitute them in this integral for the energy and get the energy of the system. So here you see an expression that looks kind of daunting, but all there is to it is just the sum of the kinetic, thermal, and potential energy. And I parameterize it using by dividing the energy here, which is a dimensional quantity, by the typical scale of the gravitational energy.
Two questions.
Yes.
What are we seeing exactly on the figures on the right-hand side?
So these are the dimensionless, the self-similar profiles for the density, the speed of sound, and the velocity inside the shock region.
Okay, and what does it mean, gamma of 1.01? I can't see a situation where you have such a low gamma.
This was something that was requested by the referee, but this could, for example, represent the case where you have copious pair production, for example. So this would be the case where there's some mechanism that's extracting energy from the system, but it's not adding to the pressure. So if you have reionization or if you have pair production, would be cases where the effective adiabatic index would be lowered.
It has to be a huge amount of pairs. You're basically producing Newton only pairs in this one.
Yes, yes.
So you must have energy which is above the threshold energy. So it can only work under certain conditions.
Yes. Again, the whole point here is just to show what the effect of different values of gamma will do to the profiles, because later on I'm going to show that actually when you have turbulence you would get a larger, not a smaller value of the gamma. But this just goes to show what changing gamma would do. So what I've done here is I changed the value of chi. So this is the ratio between, just to remind you, this is the ratio between where the fluid element came from and where the shock front is. And I measured the energy parameter here for different values of gamma and chi. And what I found is a complex behavior. So for low values of the adiabatic index, I find that there's minimum energy. Below a certain energy, there's no stable solution. If you try to explode a star with less energy than is predicted by this model, then it would just collapse instead of expanding. Above the certain threshold, when the adiabatic index is above 1.3, then you find that you can get solutions with arbitrarily small energies. But the problem there is then when you sum over the mass, you find that some mass is missing. So some mass has accreted onto the central object. You don't conserve mass. And in this way, what the central object does is it just drains all of the material from the shock region. So these two processes define for every value of the adiabatic index, they define a minimum amount of energy.
What is
And I
chi
plotted
here?
this. Sorry?
What is chi here in the right panel?
Oh, so this is what I showed earlier. This is the ratio between where stuff comes from, the initial radius of a fluid element, and the radius of the fluid element when it encounters the shock, right? Because it starts moving under gravity before the shock reaches it.
Yeah.
And what I'm showing here is that this threshold energy decreases as you increase the adiabatic index. So when you make the equation of state stiffer, it's easier for it to explode. And in some cases, you can see that you can even explode a star with less energy than is required to unbind all of the material, in which case some of it has to remain bound to the central object. Now, to understand this behavior, we can talk about something that should be more familiar to everyone, and this is traffic jam. So imagine that you leave for work, but for some reason you leave later than you planned. Because you left because you left later, then by the time you get to the road, it's more packed. There's more traffic jam, and because you move slower, even more cars are in the traffic jam. And if you kept it on, then in principle it could diverge. And this is what we're seeing, and we're seeing a similar process happening in the case of a supernova shock wave. If for some reason the shock is delayed, then it gets bombarded by it has to contend with more material that's coming from a larger radius, and it's moving faster because again it came from a larger radius. So the longer you take to break out, the more mass you have to the more pressure you have to balance. And at some point it diverges, and this is why there's a sharp cutoff that divides the successful supernovae from the failed supernovae. Okay, but this doesn't explain why changing the adiabatic index would change things. So here I'm presenting a physical interpretation that explains why this is the case. Now you need to understand that adding turbulence or changing the adiabatic index on itself doesn't add more energy to the system. But what it does, it makes the energy distributed in a more energy efficient way. So look, for example, at how the energy, what I'm showing to the right, regular set of Taylor solution without gravity. And I'm just showing how the mass is distributed for different values of the adiabatic index. And you can see that as you crank up the adiabatic index, the mass is distributed in a more uniform way. So for very low values of the adiabatic index, all the mass is concentrated close to the shock front, and you increase this, then you push some of the material further down the line. Now, because the velocity profile is homologous, the more mass you move to the center, closer to the center, the lower the kinetic energy becomes. And the same thing goes for the potential energy. As you move more material close to the center, you lower the gravitational potential energy. Now, yes.
I'm seeing it in a simpler way, to my opinion, right? You're increasing the adiabatic index means you're increasing the pressure. So you just have more material just cross the shock. It just puts pressure, so it just pushes the material away from the shock.
What do you mean away from the shock? All the material that reaches the shock is going to cross the shock and be part of the shock region.
Cross the shock, but it's not going to stay there because there is some pressure from newly coming particles, so it will just move backward and
wait, I'm sorry, I don't understand. If you have a fluid element that crosses the shock, then it adds to then it becomes a part of the shock. If you have more pressure, then it's bad for you because it's going to push it's going to squeeze all the material close to the shock front, which is what you don't want.
Then maybe I don't understand what you're up to. If you're looking, what you show here is basically that when you're increasing the adiabatic index, you have the distribution of material behind the shock is more the material behind the shock is
shallower.
What?
It's shallower.
It's the opposite, no? You have more material. More material is being away from the shock. Right, as the adiabatic index increases.
Oh, you're pushing it inside.
Yes.
Yeah, but the thing is that the pressure gradient is outside. The pressure gradient is from the center towards the the pressure is lower at the center and higher at the
That's the shock front, right?
yes, yes, sorry, the gradient, yes, the gradient is this way. Yes, sorry. The gradient is the opposite, right? Because we have to move stuff from the yes.
Right.
Right, but in the
I
end
don't
you
see-
get the same. In the end, you get the same effect, right? Instead of all the material being squeezed close to the shock front, it's more uniformly distributed throughout.
Now I'm trying to understand your statement that this is equivalent to the effect of turbulence. Because what turbulence does,
That well,
essentially you're distributing your energy among different modes.
but you also distribute the mass.
When
you look-
Asaf, maybe we should first get to the slide where he talks about turbulence.
Okay, go on.
Okay, so this is coming back to the connection to the turbulence. So as Asaf mentioned, what I've shown so far is just a one-dimensional model, and turbulence is intrinsically a high-dimensional effect. But what I argue is that increasing the adiabatic index is effectively like strengthening the turbulence. And there are two ways to explain this. So one of them is that turbulence tends to distribute the right, as we said, if you have a low adiabatic index, it tends to compress all the material close to the shock front. And if you have turbulence, then it tends to scatter it. So scattering it is effectively like it would give you the same effect as increasing the adiabatic index. And another way of thinking about it is to consider turbulence as being made of these eddies. And just from conservation of angular momentum, if you try to compress an eddy, it would behave like a gas. The pressure response would be like a gas with an effective adiabatic index of 2. So Asaf, does this answer your question about the connection between turbulence and the adiabatic index?
That I see, but there is something which is not considered here, and it's the increase of the surface of the shock wave because of the turbulence.
Of the surface area?
Yeah.
Yeah, but it
when
doesn't have to be
when you have a turbulence, then I think that the whole point is that when you have a turbulence, then the shock wave is not just propagating like in 1D, right? It's not just a function of R, it's a function of R and theta, or R and theta and phi.
Right. But then, you can enclose. But then, if it's moving out, you can enclose. You can enclose this corrugated shape that I showed earlier in a sphere, and everything, all the material that crosses the sphere is going to end up at the. It's going to end up at the surface.
Essentially, yes, but then I think effectively what you're really doing is you're increasing the surface. I think this might have a stronger effect than that. I'm not sure about that.
It's going to have an effect, but it's going to be localized. So there is this effect, but then it can't move. But this will be localized. It can't move the whole. It won't affect the supernova as a whole, right? It's going to some regions that are concave are going to move faster. Some regions that are convex are going to move slower. So it'll only introduce localized effect, not global effects. And I understand your comment, but I don't think it's going to be. I don't think it's going to affect. It's going to solve the problem of explodability. Moving on. So again, this is a very simplistic model, and what I intend to do in the future is improve it by introducing turbulences in a more consistent way, by introducing diffusion. Now again, like gravity, when you introduce diffusion, in principle you break self-similarity because you introduce more dimensional constant. But there is a way to introduce turbulence in a way that doesn't break self-similarity. And you can do this by, for example, making the adiabatic index be proportional to the product of the shock front and the shock velocity. And this is a little bit similar to the alpha model that's used to describe accretion disks. And this is something that I've already done some preliminary work with some student here about. And we show that when you increase the strength of the diffusion coefficient, the shock does tend to move faster. But again, this is something that we need to develop further in the future. Now, I should mention that once we solve this problem, then one of the benefits is that we can also get an estimate for the accretion rate onto the central object. And this would help us determine the masses of these objects and hopefully in the future, it would enable us to decide between the different computational models and decide which one of them is more likely to represent a physical reality. Maybe break the degeneracy, the problem that fix the problem that I showed you earlier. Moving on to the next object of shock breakout. So far we talked about what happens at the surface, at the very center of the star. But
what are the temperatures that we are working with here?
Sorry?
What is the magnitude of temperatures at the shock that we are working with?
So again, I don't consider shock as the temperatures explicitly, but right, it's something you would get. It depends on it's something, right? It's determined by shock physics. So it depends on like how much mass you get and what regime you're in. If you're metal dominated or radiation dominated, but of the order of upwards of could be billions of degrees, I guess would be typical. But again, it depends on the progenitor. It's not something that I considered explicitly because it doesn't enter the fluid equations.
I'm afraid in the relativistic equations and adiabatic equation of state, taking adiabatic index to be less than 1.33 may lead to unphysical results. So
you're saying, yes, you're saying that it could be, yeah. So there are a number of reasons, a number of ways where it can drop below 4/3. That I agree. But again, my claim is that you can to some extent fix it. You can compensate for it if you have a turbulence, because I made the case that you can effectively increase the value of gamma with enough turbulence.
I have a question.
Yes.
If I understand correctly, what you're saying is that you don't actually need 2 or 3D to explode a supernova. You can explode a 1D star if you just replace this turbulence by some effective degrees of freedom, or increasing the number of degrees of freedom locally with some adiabatic index. Could you then just redo the 1D simulations that had failed before with a different gamma and get explosions?
So people have done similar. So I haven't done this, but people have done similar things. So what people usually do is that they take one-dimensional simulations and they take some prescription. They calibrate their models with the 3D models, but then they just add more terms to the 1D flow equations. So instead of just having conservation of mass, momentum, and energy, you also have a diffusive term.
Do they explode?
Sorry?
Do they explode?
Yes.
Okay.
In some cases, they explode. And in many cases, what they do is they explore the range of parameters, the strength, or at least how the explodability is depends on the strength of this diffusive parameter. Now, moving on to the next topic of shock breakout. So as I said, I mostly focused on what happens at the center of the star. But if you manage to produce a successful supernova, then you want to have a shock wave that propagates all the way to the edge of the star. And when it gets very close to the edge, then photons start leaking out. And this would be on a very thin layer. This could be like 10 to the -5 of the radius of the star. And these photons that emerge out of the star would be the first electromagnetic signal of a supernova. But what's important about it is that when they're emitted, the star is still intact. And this is why it carries a lot of useful information about the progenitor. Now, the hydrodynamics in this case are complicated because what happens there is that when the shockwave gets close to the edge of the star, it sees a declining density profile. So the velocity increases. And you can, there's a very simple mechanical model that explains what's going on in here. So this is a demonstration that you might have seen in physics classes, or maybe done it yourself. It's called the Galilean cannon. And basically what you do is you put 3 balls on top of each other. So let's imagine that the top one is a tennis ball, and then you have a basketball, and then there's a bowling ball. And when you drop them, the tennis ball would bounce to a height that's much higher than what you started with, right? If you just bounced a tennis ball, it wouldn't get higher than what you started with, and here it does. And basically, this whole process is able to concentrate a large amount of energy in a small amount of mass. And a similar thing happens when the shockwave reaches the edge of the star. And when you get to the edge of the star, not only the hydrodynamics, but also the radiation transfer is also complicated. And this is because you can be in regimes where you're out of thermal equilibrium. So this is here, I'm showing a figure that I made for shock breakouts in tidal disruption events, but the same physics applies to supernovae. So you can just by looking at this figure, you can see that depending on the density and velocity of the shock can be you can be in one of 3 different regimes. So you can over on the left you can see the matter-dominated regime. Here's the in the middle is the radiation-dominated regime. Over to the right is the pair production regime, and in between it's hard to see, but you're in this is usually where many supernovae are. Is the photon-starved regime. You're in a situation where you don't produce enough photons to reach thermal equilibrium, and as you and then you converge to a different kind of photons can easily thermalize, but you just don't produce enough of them to reach thermal equilibrium, black body equilibrium. And it gets worse as the velocity increases, then you have less time to produce photons, and you need to produce more of them. So you're driven even further away from equilibrium, and the temperature here rises very fast. Now, because of these complications, most of the work done so far have focused on a simplistic case where the shockwave is almost parallel to the surface. So I'm showing here to the left some of the first analytic works on this topic. To the right, I'm showing a spectrum produced from computer simulations, but all of these assume that the shock is parallel shock, that the shock is parallel to the surface of the star. However, we know from observation that this is not the case. We know, for example, that when we see supernova remnants, we see that neutron stars get kicks, and to accelerate neutron star in the sun direction, you need to break spherical symmetry. And we also see a polarization from certain supernovae. So this is another indication that spherical symmetry is broken. We also know that some stars can spin, some of them even very rapidly, and this can distort the shape of the star. And again, this would break spherical symmetry. Now you could say, well, most cases these deviations from spherical symmetry is small, so maybe this would just add a small correction to the existing prediction. But this is actually not the case. So here I'm showing a very preliminary work by Chris Metzner here at U of T, where he shows that under certain conditions, if the shock is oblique enough, then you actually have a completely different flow profile. All the effects that I mentioned earlier just don't happen anymore. You don't have the acceleration close to the surface of the star. You have a completely different profile. And if this is the case, that this invalidates all of the previous predictions. And here's another work that I've already made some first steps in the study of shock breakouts. And this is by looking at the opposite extreme. So as I told you so far, all previous work looked at explosions that happen close to the center of the star. So we considered what happens when the explosion is very close to the edge of the star. And there, I'm showing here a simulation of what such an explosion looks like. And you can see this is very similar to a cratering event. This is like a meteorite impact. And from this, we were able to produce, here I'm showing the light curve from such an explosion, but we were also able to produce spectra, or the evolution of the temperature. And the future challenge would be to see how you can take these two extremes and interpolate them to describe what happens for a typical case where you have a small deviation from spherical symmetry. Now, so far, these studies have observations of shock breakouts have been very sparse. And one testament to that is this figure is shown in the figure to the right. This is one of the best light curves for shock breakouts that we have so far. And these were produced by an amateur astronomer that was just lucky. But this will change in the near future because of the construction because of upcoming missions, especially time domain missions like the Vera Rubin Observatory. So this is going to be an observatory that scans the sky to get a very deep image of the sky to a magnitude of 24, and it's gonna subtract images to look for changes. But even better than this is the launch of Ultrasat planned for 2023, which is going to outdo the Vera Rubin Observatory by about an order of magnitude. But not only that, it's gonna work at a higher cadence, so it would be able to detect shock breakouts much closer to when they happen. And because it operates at a different band, then it's supposed to detect these at a rate of one every month or so. So it's going to be it's going to provide a wealth of data.
It's
And
24, unfortunately.
24 already?
We
Okay, so I
wish
have
it
to-
would be 23, but yeah.
Okay.
not 21.
That's
And
a lot,
I
okay,
think
okay.
LSST, the cadence of LSST is not going to be that good, actually.
Yes, it's probably from my rate, it's roughly one every 3 days. It's going to
Yeah,
scan the slides.
so I'm not sure how they can get, they would have to be very lucky.
Yes. So anyway, okay, so I have to update it to 2024. Thanks for the comment. So one benefit of this model is that it also has the benefit of providing a candidate model for, I might explain, a new kind of transient, of something called fast blue optical transients. This is one of the cases where most of the knowledge about an astronomical effect is encoded in the name. So these transients look very, very much like supernovae. So they're very fast, they're very, very bright, and they decay with time. But they decay on a timescale that's very short. So you can't explain it with radioactive decay. So the consensus now is that they're engine driven. So what you see is is some rapid release of energy and and its evolution without recourse to radioactive elements. And one idea that I had is that if you have an explosion that happens close to the surface of the star, and then there's some trade-off between duration and wavelength. So as you move it closer to the edge, then it evolves faster, but it tends more to the bluer end of the spectrum. And because it interacts with a smaller amount of material, then you don't have the problem that you have in supernovae, where you have to wait until the light has to diffuse through the envelope. If you have less mass, then it takes a shorter amount of time. So a weaker explosion close to the edge could provide a very bright transient. But still, this is something that has to be explored in the future. Now, I want to finish off.
Are there any ideas about why the explosion should start so far off center?
So we had some ideas, and well, the thing is, you don't really have to have an explosion. The model that we consider is a case where you have some explosions that happens in a common envelope. So it doesn't have to be a very rapid release. It could be just even an Eddington, even a release at an Eddington rate inside the envelope could provide a trend, could cause a transient of the kind that we think about. So, and we know that, so we don't have a complete theory of how it happens, but we know from observations of X-ray binaries and accretion onto neutron stars that they can have duty cycles. They're very erratic. So maybe just an episode of hyperaccretion could explain it. So finally, in the last few minutes, we'll try to make this quick. In the course of working on this problem of an oblique explosion, we stumbled upon what we think is a new kind of conservation law for surface explosions. So what we did is we developed a self-similar solution for a surface explosion, and if you have a self-similar solution, then there would be some relation between the velocity and the swept up mass. It's going to be some power law, and we calculated what this power law is going to be. And we found that this power law only depends on the adiabatic index. It hardly depends on the profile. So it doesn't depend on the geometry or the distribution of the density. And we find this value is somewhere between conservation of mass and conservation of energy and conservation of momentum. And because it's such a universal law, then you can apply it to a wide range of scenarios. And I'm going to overview some of them. So you can use it to, this is something we've done in another paper. We used it to describe how much mass you would lose as a result of a giant collision between a planet and a protoplanet. And you can see it in the figure here to the right. You can use it to reproduce experiments in cratering, where they basically fired a bullet into a target, and they looked at the size of the crater as a function of the velocity. And we were able to reproduce this power law index here, which have previously only been been determined experimentally. You can also reproduce the shape of the way that the ejector is scattered around the crater. This is called the ejector blanket. And we can predict, for example, the shape of ejector blankets on craters on the moon. The reason we need to go to the moon is because on Earth there's an atmosphere, and because of the atmosphere you have drag, and drag causes makes the calculation more complicated, because then it depends on the size of the particles.
What again is the ejector blanket?
Right, when you have a crater, you take all the material that used to be where the basin is, and you scatter it around the crater. So you have these hills next to the rim of, start from the rim of the crater, and they taper down as you move away from the crater. So this is what you see here. This is for the Oriental Basin on the moon. So our model predicts the shape of these hills.
Okay. What fraction of the mass, by the way, is lost? Like,
What do you mean by lost?
Vaporized, not diffuse away, to such large distance from the crater itself that you won't be able to associate it with the crater.
So this depends. So again, well, this depends on how fast the ejector is, the projectile is moving, right? Because it's going to sweep up some material. There's going to be some material that's lost to orbit, and then there's going to be some material that's. So I'll have to calculate this. I don't know off the top of my head, but most of the material is actually blown away. Is actually in the crater. There's only a small fraction that escapes, even if you have a projectile that's moving faster than the escape velocity. So most of the mass is going to be in this ejector blanket.
Okay.
You can also use this model to predict the destructive radius of the Chelyabinsk bolide. So this is a meteor that exploded over the sky in Russia in 2013. And by looking at the reports of damage per 1,000 people, they saw that this parameter scaled as R to the minus 2.4, which is very similar to the way that the pressure scales, which is 2.7 in simulations. And our model predicts that this should change like R to the minus 2.6, which is very similar again to what they see in simulation. Just that we didn't need a simulation; we just had an analytic theory that predicted it. You can also use this to make calculations that are related to asteroid collision avoidance. So here the idea is that if there's an asteroid heading for Earth, you blast it, you make an explosion somewhere on the surface, and you deflect it this way. And you can see that our analytic model, produces a value that's very similar to what has been measured in computer simulations of this process. And finally, I want to mention a study of mine that was featured on the popular science magazine, New Scientist. And here the idea is to use the moon as a dark matter detector. So one of the models for dark matter is primordial black holes formed in the shortly after the Big Bang. And what we showed is that if there's an impact, if one of these black holes impacted on the moon, you would get a crater that looks different from a regular impact. And I'm showing here to the left some computer simulations of this effect. And you can just by eye see that the density distribution is different between the regular impact shown to the left and the black hole scenario shown to the right. So with this, I'll conclude. I'll just say that there are many open questions regarding the evolutions of massive stars and the thing that they turn to as a result of the explosion and the relics. And I've shown how I can use a combination of numerical and analytic tools to study these problems. And as a final note, I'll say that the same tools that I developed are useful not only in the study of compact objects and massive stars, but they're also applicable to a wide range of problems in astrophysics, including planetary collisions. So with this, I'll finish and I'll take any questions.
That's all. Thank you, Almog. I have a first question just about what you just said about black holes hitting the moon.
Yes.
What would have happened to those black holes after they hit the moon?
Not much, because they interact, right? You only interact with things in the Bondi radius. And if you drill, and the Bondi radius is tiny, it's like, I don't know, something like a micrometer. So right, it's like you drill it's a very long but very thin hole along the moon. So they hardly lose any mass. They hardly accrete any mass from this interaction.
So could we look for them on Earth as well?
In principle, yes. The problem is that on Earth you have the atmosphere and you have tectonic processes. So it doesn't survive for that long. So the reason we turn to the moon is because it can survive for long enough to be detected today. But in principle, it would work. The same method could apply to any other body in the solar system that doesn't have tectonics or an atmosphere.
Okay, and another question.
Mm-hmm.
If successful explosions of supernovae are so delicate in conditions, should we expect astrophysically failed supernovae to be very common, or as common as supernovae?
So they're not as common because let's go back to this figure. I think it's a bit misleading because it seems like all these masses are equally likely, but right, you need to remember that you have the mass profile is biased towards the low masses. So even though it seems like you only get successful explosion in this part of the spectrum, you would expect most massive stars to successfully explode, right? Stars that are 20 solar masses are much rarer than 10 solar masses. So even in cases where most of the spectrum seems to collapse, you would still see most of the stars, most of the stars around you would be stars that successfully explode. And also, it's not clear that it's so delicate. We know that our models are very delicate, but it doesn't mean that the stars are not bound to our perceptions.
Okay.
Yeah, I want to go back to your 1D model
Yes.
of explosion. You show that you can get analytical solution provided that the density behaves in a certain way.
Yes.
But the typical stars that we know are progenitor stars for supernova, there are some estimates of their density profile. And to the best of my knowledge, and I'm not an expert on that, they do not behave in this very simple way that you showed, but rather
they only have to behave, right? It's only the part that's closer to the center. Once you've reached a rate, once the radius is much larger than what you started with, then the explosion is already successful. You only care about what happens very close to the center, and you can see, for example, here that these profiles are very similar, very close to R to the -2. So I know, for example, that if you go to the low end of the high mass, so stars between 7 and let's say 9 solar masses, then you get a very different profile. Then the profile is more like an exponential, drops much more rapidly. But
you show if this is the profile. I mean, you're showing here that the profile looks like an R-2, something like 100, 200 kilometers and above.
Yes.
But then when you show the simulations, you show that the 1D simulation, the shock stalls at about this radius, if I recall properly, something like 100 kilometers or so, and then it just falls back in.
Yes.
Right. So why is it true to assume that this is that's the profile if the shock doesn't reach far beyond that? Or maybe I missed that part.
No. So sorry. Don't understand the question. You only care about what happens, right? You only care about what happens to the profiles at roughly this radius.
No, I agree. If you reach this radius already, then you can go on, but you won't reach this radius in the first place, right? This is what the 1D simulations show. Now you say, okay, I can add to these simulations some.
Well, this is what you stall.
Yeah, it will be stalled at around 100 kilometers, right? If I remember properly from one of your previous slides. But if you can go back to the slide that you showed the simulation results. But so you really care about what happens at earlier stages than that, right? If you already crossed that, then it's okay, then you can proceed, then there is no problem really.
Almog, are you here or did we lose you? I lost his video and I don't hear him.
Shocked by the question. Hopefully, yeah.
Almog, hello, are you back?
I'm back. I see.
Yes, sorry, I don't know what happened. I just got disconnected.
Right.
So as I said, the deciding moment is about 200 kilometers.
Right. So I thought that, the simulations show that if the shockwave managed to cross the 200 kilometers barrier, it will explode.
Mhm.
Right. So the main problem is before that.
Yes,
Right. But
or around
before
that, right? Because all the simulations stall at about this radius.
Right. So, but the point is that before that, you cannot assume that the profile has this parallel shape, only at a larger radii.
Okay, but again, from here we can see even just from.
I don't see your screen, by the way, right now.
Wait, I'll share it again. So here, if you look at the lower right, you look at the lowest line, the earliest line. You can see that the profile extends all the way to 100 kilometers.
Yeah, but if you're looking at the okay, that's different times.
Yes.
I see. All right.
So this is the best indication, right? Because this is the earliest time. So this is the point where the shockwave hasn't reached this point yet. After the shock reaches that point, then of course it's going to be different.
Okay. All right. Thanks.
Any other questions?
Any of the students, postdocs? Ofrek, I don't know if you say anything. I cannot hear you.
I suggested awarding an award to the student or postdoc who asks the most questions. Right now, there's very little competition. Any more questions, students, postdocs?
I have a naive question. So
Yes.
if you want to understand physically what exactly leads to the explosion when the gravitational attraction is balanced by the exclusion principle when the star explodes before explosion. So do you mean to say that these are thermal explosions when the shock is heated up and then it leads to kind of expansion?
So what do you mean by thermal explosion?
Means what is the nature of explosion in supernova in this case? What drives the explosion in the first place?
Oh, so the idea here is that you have a core that collapses, it turns into a proto-neutron star, and this process by itself produces a lot of energy. Mostly in the form of neutrinos, which escape, but still a fraction of them does get captured, and this is what drives it's this release of energy that produces an explosion and the first shockwave that propagates outward. So does this answer your question?
Yeah, but I'm
Okay.
just trying to understand, is this energy sufficient enough to counter the gravity?
So that's also what I'm trying to answer. But we know that without turbulence it doesn't. With turbulence, it is successful in overcoming gravity. And what the point that I'm making is that what turbulence does is it doesn't add more energy of its own. It just lowers the bar.
Yeah, turbulence in itself is a dissipative process, right? It dissipates the energy, whatever the flow already has.
So what do you mean by dissipate the energy?
Turbulence is a dissipative
Right,
physical phenomena.
Right, but in this dissipate doesn't mean that it dissipates. It just says that it takes collimated motion and turns it into heat. So everything stays in like the amount of energy. If you just have turbulence, the amount of energy in the shock region remains the same. It just maybe has different forms.
Yeah. Okay.
Can I ask something?
Sure.
Of course.
Now that there's a reward, now I'm just joking. I was wondering, by researching the explosive mechanisms, could we perhaps learn to, how do I say it, predict supernovas? Because that is basically one
advance?
of the issues, right?
Well, there's a question of how you, how to, so just to see that I understand, you talking about ways to predict that a certain star will explode in the future, or when it's going to explode in the future.
Yeah, exactly. Because like you said, we only know like 2 weeks after it happens, and I imagine we lose a lot of information from the supernova.
Yes. So from this model, you can't. The way that people, so you can't do it for all stars, but some stars we know experience an episode of a very vigorous mass loss. So sometimes you see stars that cough up a large fraction of their envelope. So, well, there's a story behind it, but there's evidence that in some cases what happens is that you have a star, for some reason there's an explosion. The explosion is not strong enough to destroy the star. You just knock off a shell, a very thick shell of the material. Then some time goes by, and then it explodes. So there are some cases where you can predict that a star is going to explode, but this depends on if it does if there's some violent transit that happens before that. I don't know if any. Probably that's the only way to do it with optical instruments. There are some works I think that if you could measure gravitational waves, then maybe you can get more information closer to the explosion, like before the explosion itself, because gravitational radiation escapes the star before the photons. But the problem there is that unless it happens in our galaxy, I think the instruments we have now are not sensitive enough to detect it.
Okay.
I should advertise that we'll have a talk about supernova precursors here in the Astro seminar, physically at Bar Ilan on November 30th. So we'll hear more about that.
Okay, maybe you can send me an invitation as well.
It's on the website. Everyone is invited, of course.
Okay, I'll check it out.
Any more questions? Going once, going twice. Let's thank Almog again. Thank you. I'm closing off the recording now.